splits it into 4 pieces, and now we have the relay optics. You can see the light converging. Right there is where the correction is made. Once the correction is made, the light continues on to the sensors. There are actually 4 of them in the WFPIC that are mosaic together. I have one of those mirrors. As was already mentioned, WFPIC2 was, or the clone, was already under construction, and we had already built part of this. In fact, the part that you saw there was already built. So we had, we actually took this optic out of the WFPIC instrument. This is one of the 4 small mirrors that you saw in the animation. And now imagine that the Hubble telescope is imaged on that small mirror, the Hubble telescope itself, the primary mirror. This is the opportunity then to change the shape of this one small mirror, correct the miniature version of the Hubble telescope. And from then on, we've got a complete, perfect correction. We recover the full field, and we recover all the resolution that we initially planned to have. Some variation of this method has been used on all the instruments. WFPIC2 was the first, but all of the instruments since WFPIC2 have an internal correction that uses the same principle. So it's very familiar to us all by now. All right, so there were many tests we could do on in the laboratory to make sure, or be as sure as we possibly could, that we've done it right. But we could never know until it was actually on orbit taking pictures. So the next image is a comparison. On the left is the best image we'd received from Hubble prior to the correction. And on the right, well, let me explain. What we're looking at is the nucleus of a galaxy, the 100th galaxy in the Messier catalog, called otherwise known as M100. It's about 53 million light years distant, and we're looking at the central nucleus. It's clear, comparing left and right, that on the right we've recovered a great deal of detail, so it's obvious that we were heading in the right direction. The next step, I'd like to put that picture in context. The next image is that same M100 galaxy, but now in the context, in the surrounding black and white image is actually an image taken from a ground-based observatory in black and white. The inset that shows some color, some true color, is the full field of the wide-field planetary camera. At the center, you see that nucleus that we looked at just a moment ago. In the surrounding field, though, we can make out about 4,000 individual stars in that field. Among them, something like 1 in 100 that we see is a Cepheid variable star. This is the distance indicating stars, the type of stars that Edwin Hubble himself used working on Mount Wilson nearly 80 years ago at Mount Wilson to measure the distance to the Andromeda galaxy, which is only 2.5 million light years away, about 20 times closer. What this image shows right away is that we have extended our reach. Hubble has, with an image like this, we've extended our reach, our ability to see details in distant objects by a distance of about a factor of 20. That expands our exploration field by a factor of 1,000, and this is exactly what we needed to show to indicate that some of these key programs would go forward. Next slide. This was just the beginning. Many others were taken even in that first month. This is Eta Carina. You can make out detail here of this massive star that's in the process of blowing itself to pieces. You can make out something that you might describe as an ant in a tutu. It shows you how the clouds are flying apart as a level of detail we could not see before this fix was put in. Next image. We had an opportunity to take a look at supernova 1987A. It's something that happens more or less once a century in a galaxy. This actually is 170,000 light years away in the Large Magellanic Cloud, and it's an illustration of the timeliness, our ability to see something that will, in fact, destroy itself. That central object, which is the exploding star, will eventually, and in fact we are seeing it even now, is beginning to destroy that structure that was pre-existing. All right, so that was the beginning. There have been the beginning of something on the order of 135,000 images that have been taken with the WFPIC2 in the past 15.5 years. This instrument has orbited with Hubble over 84,000 times. And we're it's taking data even as we speak, and I think we'll hear about the very last image, which is going to be taken tomorrow night, I think. So it's still there. It's old, reliable, but it's time to retire it. It's time for it to come home. One last look. There's one more image, which was taken just last week, and this is a planetary nebulae called K455. It's shown in the combined light of nitrogen, hydrogen, and oxygen, and it's an illustration that old camera is still there. It's still working, still cranking out significant science. At this point, we're going to say we're going to celebrate. This has been a 15-and-a-half-year very successful mission. We're thrilled, and it's a time for renewal. We know we're hearing lots about the new instruments that are going to bring